Hello there, my name's Mark Tschopp and welcome to Empowering the Force. This is a continuation of an earlier part where we started into neural networks, and now we're going to move into some of the training aspects, so talking about some of the concepts behind how you train neural networks. So without further ado, let's go ahead and dive right in. Okay, pulled up our screen. So again, we talked about the different concepts that we're going to cover or different topics within neural networks. And we talked a little bit about how neural networks work and what were these nonlinear functions or activation functions that really power the ability to learn these very complex relationships. And now we're going to step into the training part. So I've broken it down into different sections, and I think the backpropagation part is going to take a sufficient amount of time. So we're going to go ahead and cover just that within this video. Okay, so how do you train all of those parameters? I mean, so far we've just done very simple examples with linear regression, with logistic regression. Now we're going to move on to neural networks that can often have parameters that are tens of thousands, hundreds of thousands, millions, even billions of parameters. So how do you go about training all of those parameters? And it really comes down to this first one, which is the miracle of backpropagation. I mean, maybe miracle is a little too strong, but certainly it was a big breakthrough in the ability to actually train neural networks. Part of this is because when you look at the history of these different models, there were people talking about perceptrons. Again, just another name really for these neural networks. Back in the 50s, 60s, but there were a lot of problems back then with how these perceptrons were viewed, and also just the ability to actually train all of these different model parameters within these neural networks didn't really exist. And so it really took up until, again, 80s, 90s, before someone actually figured out how would we compose a system where we were able to update and train all of these model parameters. And really, that's what's called backpropagation, and that's what enabled all these very deep neural networks to suddenly be trained. So that really was a turning point in these more simple machine learning models starting to move towards these more complex neural networks. So I don't know if I mentioned it or not, but backpropagation is really, it's built upon calculus. So for those of you that want to skip ahead because I don't want any calculus, then that's fine. But for the rest of you that want to understand a little bit about how backpropagation work, we're going to have to go back in time to Calculus 1. So first thing I mentioned here, you remember that chain rule that you learned in Calculus 1 that you never thought you'd learn or never thought you'd use again? Well, actually, backpropagation uses that. And in a smart way in order to make these neural networks operate. And again, it makes it operate through training these model parameters within the neural network. So if we go back to the chain rule, just to simply describe it, we have here, again, y is a function of x. This is very similar to what we've been talking about all along. What if we added another equation where z is a function of y? So this happens all the time. And if you want to take the derivative of z with respect to x, so let's look down below, derivative of z with respect to x, you can actually break this into parts. So you can take the derivative of z with respect to y, so that would be this first or this second equation. and then the derivative of y with respect to x. So that'd be this first equation. Multiply those together, and what ends up happening is these terms actually cancel out. And what you have is the derivative of z with respect to x, which is exactly what you want. And that's really what powers backpropagation, is the ability to, compose and break this into parts so you can compute the derivative, so you can update all of these model parameters. So if we go back to this neural network here, what's actually happening? One is you have forward propagation. So you're going to feed in the inputs or the activations in the 0th layer, and you're going to successively compute activations in each next layer until you get up to the output node or nodes, and that's going to give you your prediction. From that prediction, you can now, compute. Again, here's this L2 loss function, but you can compute J, the cost function. Now, in going forward, you want to compute this prediction, y hat, but you also want to cache or store all of these intermediate values. So you store all of this is the linear part of the nodes, the nonlinear part of the nodes, the weights, and the biases. So you're going to store all of those values when you're doing the forward pass. And then backpropagation works because you go backwards. So now you're going from y's back to each of these model parameters. And you want to really update the weights and the biases. So yeah, how do you get the right parameters though? We now know that we're storing some values on the forward pass, and somehow we're updating things on the backpropagation. So we'll talk a little bit about backpropagation next. So here we go. It's really as simple as gradient descent. We had another video that kind of covered optimization and gradient descent for some simple functions. Here, let's just assume we're trying to update the weights in the 5th layer. So these red lines here in the 5th layer. The gradient descent equation tells us that we need the current weights, which we've stored, so good, that's easy to do. We're going to subtract a step size parameter. Again, that's a hyperparameter that we actually set. And then we need this derivative. We need the derivative of the cost function with respect to the weights. And so how you do that is you actually break it into parts. So the derivative of the cost function with respect to weights, again, you take the derivative of the cost function with respect to the activation, derivative of activation with respect to z, the linear part, derivative of z with respect to the weights, and now you can cross out all those intermediate parts and you're left with the derivative of the cost function with respect to the derivative of the weights. And you can do this for every model parameter within this entire model. So if you wanted to update weights all the way back in the 1st layer, so again, these lines back here, connecting the 0th layer with the 1st layer, you can take successively derivative of j with respect to a in the 5th layer. You can see 4th layer, 3rd layer, 2nd layer, 1st layer, all the way back to the weight. And again, similar to what I showed up above, all of these intermediate terms cancel out. But we've broke it into parts that are easily computable for a computer. And now, why do people talk about exploding and vanishing gradients? Maybe some of you have heard this term being thrown around. A lot of that comes from the fact that now you've got all of these different terms that are multiplied together. Imagine that one of these terms is 0 or close to 0. That would make this entire thing equal to 0. If this is close to 0 or equal to 0, then you can see what it does to this term right here. It makes that close to 0. And so what you end up with is that the initial model parameter isn't updated at all. So that's what's called vanishing gradients. Exploding gradients would be if one or more terms are very large. So suddenly when you multiply a bunch of things together and have some very large terms, this is going to make this derivative very large. And when you plug something very large into this term, now you're updating it too much. You're updating it so much that the model may actually get worse, because you've updated the model parameter too greatly. So there's a number of different techniques that are used to actually combat this, and they work pretty well. But this has been a problem in the past, and you can see why. It's because you're chaining all of these different subparts or derivatives together, and so that could lead to these sort of problems. Now, this looks very hairy. I know I've spent a lot of time on this slide, but this last part is important because when you're using things like Python, and TensorFlow, PyTorch, Keras, I'm naming different packages that you'd use within Python for neural networks. It keeps track of all of this for you. So you aren't exactly having to program in all of this. These sort of packages keep track of all of these derivatives so that they can optimize the model parameters. Let's go ahead and unpack this, one step at a time. So we have our initial equation. This is gradient descent. This is how we're going to update the weights in the fifth layer. And you can see these weights here. So the derivative of the cost function with respect to these weights can be broken apart. So derivative of j with respect to activation. So j with respect to activation. Activation with respect to z. Activation with respect to z, derivative of z with respect to the weights. So derivative of z with respect to the weights. So you can kind of see how derivative, how this kind of passes this information back to update all of these model parameters. So let's first look at this first term, the derivative of the cost function with respect to the activation. So if we look at this, this is nothing more than y minus y hat, or y minus the activation of this final node squared. So the derivative of this with respect to a, if you kind of recall from calculus, you take the exponent, you move it to the front, you copy this term, so y minus a. You subtract 1 from the exponent, so that 2 goes to 1. And then you take the derivative of what's inside. So you can see y minus a, the derivative of that is negative 1 because of that negative a term. So this is your derivative for the red component. Now this is really easy. The derivative of the activation with respect to z. So if you remember that f with the term for the derivative with respect to z, you know that the sigmoid function is just the derivative of that is a function of itself. So if we stored f of z, we can simply plug it in this sigmoid derivative term, and then we can actually, just substitute f of z is actually just this activation, and then 1 minus the activation. So that ends up being the final answer. That's a derivative. Again, this is why choosing very simple activation functions where you can compute the derivative very easily can lead to you've already stored these terms. Now you just plug it in and you've got this derivative term. And now the green part, derivative of z with respect to the weights. Well, z is the weights in the fifth layer times the activation in the fourth plus the bias. You want the derivative with respect to weight in the fifth layer. Well, b with respect to w, that's 0, so that cancels out. And the derivative of weight 5, activation 4, well, this goes to 1. And so what you're left with is the activations in the fourth layer, which again, we have stored, so you just plug that value in here. Sometimes people ask, well, what about the bias? Well, if you took that z term with respect to bias, so you would have b5 with respect to b5, that derivative is equal to 1. So if you plug that in here, that would be the derivative of the cost function with respect to bias. And this is the derivative of the cost function with respect to weight. So now that we have all of these terms computed, we've stored the activations at every layer. And so we can simply plug them in these formulas, compute the value, plug it in for this derivative part for gradient descent, multiply by the hyperparameter, adjust the weights, and there you go. We've updated it for one iteration. Oh, yes, I know. Admiral Akbar. Sorry that I had to pull out calculus. Again, I told people that if they wanted to skip ahead to the next video, they could do that. But I'm going to try to show it in a schematic too, for those of you that don't speak math. Okay, so here we go. Here's our entire neural network. You have inputs. You're multiplying them by the weights and the bias, but you're also storing them, right? That's what this cache box is. You're going to store them as you go through your neural network. So you do the matrix multiplication. That gives you z, this intermediate state. Go ahead and store that. You're going to take that and apply an activation function. And after applying that activation function, you're going to compute the prediction, y hat. You can compare y hat with y, your actual responses. And then you can compute a loss function, j. So that's how good the model actually is. Now, you can go ahead and look at all these subcomponents. So this is how you would compute that derivative for gradient descent. This first part, this is nothing more than mx plus b. Right? I mean, so this is a linear equation where you're just trying to compute the slope, and for b, it's just equal to 1. So that's how you compute the derivative here. If you recall, this is the sigmoid function, and here we go. This is the derivative of the sigmoid function. So if you stored this value, just plug it in to these, and there you go. You have your final derivative. And last, the cost function is a quadratic function. And again, we know how to take the derivative of a quadratic function, so you can compute that as well. So we've computed this derivative of the cost function with respect to weight. Multiply it by negative alpha, which is your hyperparameter, the step size. And that's going to be used to adjust these weights and biases earlier in the model. And now that you've adjusted them, your weights and biases are new, you can go back and repeat the process. So take the inputs, multiply by the weights and biases, compute an intermediate state z, apply the activation function. You can compute all the derivatives. You're going to store them, for each iteration until you need them, and then you just repeat. So this is an iterative process where you're going to iteratively update these weights and biases. And so with that, we've kind of come to the end. That's how backpropagation works, at least at a simple level. And really it's not much more complex than that. Although optimization, there's a few tricks that people have used, to slightly change how gradient descent works in order to get better optimization results. And so that's what we're going to talk about in the next video. So with that, thank you for joining. Hopefully this has explained a little bit about how backpropagation works and really shows maybe a little too much of the calculus, the derivatives, and how the chain rule actually makes this all possible. But hopefully that gives you a little flavor for conceptually what's going on in the background as you train these machine learning models, these neural networks. So with that, may the force be with you.